All right, let's talk about some initial conditions and particular solutions. What we're talking about with this is we've already seen that the equation y equals the integral of f of x dx has many solutions, each differing from the others by a constant. This means that the graph of any two antiderivatives of f are vertical translations of each other. So when you add a constant outside of a function like the plus c, it's going to shift the function up that many units up or that many units down, depending if it's addition or subtraction. Therefore, all antiderivatives differ by a constant, and it's just one graph is the vertical translation of the other. So this shows a bunch of different ones. So the integral of 3x squared minus 1 dx is x cubed minus x plus c, and there's a whole bunch of different ones for different values of c. And you can see if you pick any point on the x-axis and go up or down through the different curves are going to have the same slope at those points. Particularly if you pick this point right here, you can see the slope is 0, 0, 0, 0 for all of them. Because each of those antiderivatives is a solution to the differential equation dy dx equals 3x squared minus 1. In many applications of integration, you are given enough information to determine what's called a particular solution. A particular solution is when you figure out the value of c. Remember, the antiderivative with the c there is called the general solution, because in general you add a constant to the antiderivative. However, the particular solution is when you're able to have enough information to figure out what the value of c is. So to do that, you need only know the value of the original function for one value of x. In other words, you need a point on the antiderivative. That information is called the initial condition. For example, in figure 6.2, only one curve passes through the point 2, 4. So 2, 4 right there. It's just that curve. So as long as I have one point on the curve, I can solve for the particular solution. So if I know that this is the antiderivative and I know that f of 2 produces 4, then I can substitute 2 into that function, set it equal to 4, and solve for c. Now that I know that c is -2, I can obtain the particular solution. Big red flag here. Lots of times when students do initial conditions and particular solutions problems, they'll get to the value of c and stop. Okay. The value of c is just a particular value for c, but it's not the particular solution. The particular solution is the function with the value of c replaced with what it should be for that particular situation. Okay, so make sure you go that last step and write the answer. So find the general solution of f prime equals 1 over x squared for x greater than 0, and find the particular solution that satisfies the initial condition f of 1 equals 0. So to find the general solution, integrate, you obtain integral of 1 over x squared, which is really the integral of x to the -2. So you add 1 to the exponent, divide by the new exponent, and you get -1 over x plus c for x greater than 0 as stated. That's the general solution, because in general, you add c. Using the initial condition f of 1 equals 0, you plug 1 into your general solution, set it equal to the y value, and solve for c. And in this case, you'd have -1 plus c equals 0, so c should equal 1. And the particular solution is -1 over x plus c. Okay, I have a couple different ones here graphed, but the one in particular is the one with the point on it in dark, graphed in black there. Okay, so far in this section, you have been using x as the variable of integration. In applications, it's often convenient to use a different variable. For instance, in the following example involving time, the variable of integration is t. One of the most important steps in integrating or in integration is rewriting the integrand in a form that fits the basic integration rules. So let's try a problem out. A ball is thrown upward with an initial velocity of 64 feet per second from an initial height of 80 feet. Find the position function giving the height s as a function of time t, and part b, when does the ball hit the ground? All right, so let t equals 0 represent the initial time. The two given initial conditions can be written as s of 0 equals 80 and s prime of 0 equals 64, because the initial velocity is 64. So remember that velocity is the derivative of your position function. So using -32 feet per second, since the problem's in feet, remember way back when we first started talking about these, we said that the acceleration due to gravity of a free-falling object in feet is negative 32 feet per second squared. Well, acceleration is the second derivative of position. So I know that the second derivative should be equal to negative 32 because that is the acceleration due to gravity. Okay, so if I integrate the second derivative, I should get the first derivative. So the integral of negative 32 is negative 32t plus c. Now I can use the initial condition of the initial velocity to figure out the c value. So when no time has gone by, I know the velocity is 64. So I plug 0 in, set it equal to 64, solve for c1. You get c1 equals 64. So now my equation becomes negative 32t plus 64. But that's the velocity equation. The question asks me, what's the position function? Well, if I know the velocity function now, I got to integrate one more time. And the antiderivative of negative 32t plus 64 is negative 16t squared plus 64t plus c2. Now I also know the initial height, the initial position, or the initial condition for the height function. So using the initial height, you can plug in 0 and set to the function and set it equal to 80 and solve for c2. So c2 equals 80. So the position function is I take the general solution of the position function, substitute 80 in for my c, and you get negative 16t squared plus 64t plus 80. All right, and this is the graph right here. Now, by using the position function found in part A, you can find the time at which the ball hits the ground. Okay, if it hits the ground, what's the height? 0, because it's at the ground, that's ground level, that's 0 feet above ground level, and the function models how high above the ground the object is. So I just set the equation equal to 0, factor out a negative 16, and then factor what remains, and I get t plus 1, t minus 5. So t could be negative 1 or 5. We exclude the negative value because we're talking about time. So you conclude that the ball hits the ground 5 seconds after it's thrown. And if you back up here, you can see at 5 seconds from the graph that this is when the ball hits the ground. So example 7 shows how to use calculus to analyze vertical motion problems in which the acceleration is determined by gravitational force. You can use a similar strategy to analyze any other linear motion problems, vertical or horizontal, in which the acceleration or the deceleration is the result of some other force, as you'll see if you look at exercises 69 through 77. So here are some additional examples. Let me just run through these. So you have 2 over the square root of x. We rewrote it as factoring the 2 out and x to the negative 1/2. Add 1 to the exponent, divide by the new exponent, or multiply by the reciprocal, we multiply by another 2, which would give you 4x to the 1/2. This one, we haven't yet learned a chain rule type thing for antiderivatives, though under some circumstances there is like a reverse chain rule, and we'll talk about that when we come to it. So for now, what we're going to have to do is actually FOIL this out, okay? Because it's not just separate terms with t to a power, because it's this quantity to a power, not just t to a power. So if you multiply t squared plus 1 times t squared plus 1 and FOIL that bad boy out, you get t to the 4th plus 2t squared plus 1. Again, that was just algebra. We didn't do any calculus there. Now we take the antiderivative by adding 1 to the exponent, dividing by the new exponent, and the antiderivative of 1 is t. Simplify it, slap on your c. This one, you have a quotient, and you can't anti-differentiate a quotient, so you divide each term by x squared, and you get x plus 3x to the negative 2. Again, only algebra, no calculus so far. Use the basic anti-differentiation rules. Simplify. Don't forget your plus c. Here, you have a product. Okay, again, no anti-differentiation rule for a product. The cube root of x is x to the 1/3. So we're going to distribute that here and here. Remember, when you multiply like bases, you add the exponent. So the exponent on this x is understood to be a 1. So 1/3 plus 1 is 4/3. And you distribute the x to the 1/3 to the 4 also, and it just becomes minus 4x to the 1/3. Again, no calculus yet at this step. We just algebraically simplified it. Then in each case, you add 1 to the exponent, divide by the new exponent. And here what they did was they simplified and factored out a factor of x to the 4/3. You didn't have to do that. You could have left it as 3/7 x to the 7/3 minus 3x to the 4/3. Okay, that's what you get there, plus c. All right, well, that's it, guys, for this section. Please continue on to your assignments, and as always, reach out to me if you have any questions. Take care.